one of the things we can look at between two vectors is the angle at which they diverge away from each other, the angle of divergence. And that is represented by theta here in this example. That angle of divergence is given by this formula. So cos theta equals the vector A dot vector B over the size of vector A times the size of vector B. This A dot B thing is the dot product or the scalar product, and is the subject of our video today. It's worth just noting at this stage that if you are looking at the angle between two vector lines, you're using the thing which dictates the direction of that vector, i.e. the direction vectors. But it's exactly the same problem, so we're not going to do two videos on this, we'll just do the one. So we're actually going to derive the dot product, which is, I think, probably one of the most helpful ways of figuring out what it is. And you notice that we were calculating an angle and we ended up with the cos in there. So that's giving us, hopefully, a massive clue that actually we're going to be using the cosine rule to generate the dot product. So here I've got the same problem I had before, but I've just reduced the lines so that we're now in a triangle. And we've got the vector A, which is represented by A1, A2, A3, the most general vector we can draw, and B by B1, B2, and B3. Now, if we're trying to find an angle, we know that the cosine rule tells us we need to have three sides. So I'm going to have to calculate this side AB. And AB, we know, would be B minus A. So it would be B1 minus A1, B2 minus A2, and B3 minus A3. And that's from A-level. Also, to calculate the angle within a triangle, it's no good having vectors we don't understand that. What we have in the cosine rule is the lengths of the lines. And so in each case, I should be able to work out the length of this line in terms of the variables we've got here. So A1, B1, that kind of thing. Now we know that the length of these lines would be Pythagoras. And so it should be possible to do each of our vector lines as little lengths. Now I'm just going to pause and get those finished for you because I don't want to waste any time on them. Right, we now need to substitute in all of these expressions that we have here into the cosine rule to try and find the angle. So the cosine rule says that the side opposite the angle is equal to the other two sides squared and summed minus 2bc cos A, a formula I'm sure you're incredibly familiar with. Right, the side opposite our angle is our A to B side, so that's going to go in and squared, and of course that negates the square root, so we're just left with B1 minus A1 squared, B2 minus A2 squared, B3 minus A3 squared. We're going to keep going and filling in the rest of that formula. Okay, so here we have the entire formula written out. Notice for the BC bit in the, over here, the 2 BC cos A bit, I have just left those as the lengths of the two vectors. And that's in part because I was running out of room, but also because we could write those in as the square roots, but we're going to want them back as their modular symbols later on down the line. But the length B is the length of the vector A in this case. It's slightly confusing, I appreciate, but those are the equivalent places there, and hopefully the colours has helped sort that out. Okay, well this little chunk over here is looking quite a lot like the thing we would want, which is, well, good, I guess, for a start. And so what we're going to now do is just have a look at what cancels in the remaining terms that we have. Now, at the moment, absolutely nothing, because on this left-hand side, I have these expressions that are in square brackets, and that's no good for us. So I'm actually going to spend a little bit of time expanding out these terms here. So obviously the first bracket would expand, as I'm sure you know, to b1 squared minus 2a1b1 plus a1 squared, and we would get the similar expressions for each of the other terms. So in our expression now, I haven't written off the far end of the right hand side, that bit is absolutely fine. I'm noticing that I've got a couple of terms here, just a few, that I can cancel out. I have a b1 squared on both sides of my equal sign, so that can go. I have a b2 squared, that can go, a b3 squared. And I feel a little frustrated because I've just written all of these out, but I more importantly enjoy the cancelling process. So I've got an a1 squared that can go, an a2 squared that can go, an a3 squared that can go. And I am left with then the following terms: minus 2a1b1, minus 2a2b2, minus 2a3b3, and that equals only minus 2 mod A mod B cos theta. Well, hopefully you can see now that if we cancel by minus 2, we're left with a1 b1 plus a2 b2 plus a3 b3, equaling the modulus of A times the modulus of B times cos theta. And by dividing by the modulus of A modulus of B, we actually arrive at our formula, or at least the structure of the formula. And this has now given us what the dot product is. The dot product, therefore, A dot B, is the first term of A multiplied to the first term of B, add the second term of A multiplied to the second term of B, and add the third term of A multiplied to the third term of B. Now, I could have just told you that, but hopefully by going through this process you can see where the formula for the dot product came from and why perhaps it's a little bit nicer to use the form A dot B rather than having to write this expression out every time. So just to summarise then, this dot or scalar product A dot B is the first term of A multiplied to the first term of B and added to the remaining terms in multiplication. And we use this as part of the formula to find the angle of divergence between two vectors or two vector lines, where we would use the direction vectors to dictate that angle. Now, we can use this even further. If vectors are perpendicular, for instance, then the angle between them we know, of course, is 90. If I plug that into the equation that we just worked out, so A dot B over the modulus of A, the modulus of B, and I put theta equals 90 in, I'm going to get 0 on this left-hand side. So I'm going to get that 0 is the expression on the right, and of course multiplying up by that mod A mod B gives me that for perpendicular vectors, the dot product, A dot B, is 0. And that's a really, really useful little rule that you will need and you should have in your toolkit for problems. So this is one of my absolute favourite questions I think that's ever appeared on an exam paper. This is from OCR's 2016 C4 paper, and I just loved how many different topics they'd managed to shove in this thing. It looks a little overwhelming at first, or it can look a little overwhelming. Hopefully it looks like something you want to get your teeth into, and we're going to do just that. So can I suggest that you pause this video and you give this question a go for yourself. Make full use of every piece of information they've given you. Okay, hopefully you've paused the video and you've given this question a go for yourselves. Like I said, love this question, and I love it because all the information I need is actually in here. We're told that AA and OB are perpendicular, and we know from the previous slide that that means that the dot product between the vectors OA and OB must equal 0. Now, no matter how chunky those vectors are, we should be able to calculate the dot product between them. So that's 3 sine alpha to cos alpha minus 1 being multiplied by in the dot product form with 2 cos alpha, 4 sine alpha, and 3. So hopefully that is something that you did. So that will be 6 sine alpha cos alpha plus 8 sine alpha cos alpha minus 3 equals 0. That gives us 14 sine alpha cos alpha equaling 3. Now, to solve that, hopefully you've spotted that that is the double angle formula for sine, but 7 times too big. So this is 7 sine 2 alpha here, equaling 3, in which case sine 2 alpha is 3 over 7. Solving this equation gives us the values alpha equals 12.7 and alpha equals 77.3, and of course you'll want to show some working when you write down your answer. So for part B, we have just a really nice bit of almost GCSE maths at this point. Our triangle OAB is right angled because we know that the vectors OA and OB are perpendicular to one another. So we're just using a half base times height here, where we need our base and our height to be the lengths of those vectors. Well, we'll do that with the magnitude. You could do that algebraically, as I've done, and then substitute in your value of alpha. Or you could, in this case, substitute in your value of alpha, so substituting in your 12.7, your smaller value, and then taking the numbers and calculating the lengths. But either way, you get an area of 4.22 square units. And that is it.